So we'll revisit that in a moment as we get into the next sim that this is feeding into. But before we do that, we might as well look at the meshing. So let me activate these. And it's a really good idea to cache things like this, especially flip sims, which tend to be very slow, because then you can do the meshing at your heart's content and not worry about run up or anything like that. So move forward in the timeline a little bit. VDB from particles, and then that's feeding into a VDB reshape set to close. And what that does is it just gets rid of a lot of the sort of spherical parts of the sim. Another VDB reshape that's set to erode, which just shrinks it a little bit. And as you can see, we're not too worried about resolution on both our flip sim and in the meshing because it's a component of the effect. And this is actually just one step of the meshing process because we're going to mesh it this time and then we'll mesh it again later down the line, along with all the bubbles and other simulation elements.
Could we pause for questions for a sec?
Absolutely.
Okay, awesome. So Philip is asking, why are the points deleted by @ptnum and not by @id, the remove point function? It could be either, right?
It could be, yes, it could be either. The ID it doesn't really matter. It could be either. It doesn't really matter. The ID is just giving us a random number of all of our points. And then ptnum just looks at the points in general. The only reason I am using ID here is it's not changing from frame to frame. Does that make sense?
That's important. Yeah.
Yeah. The ID doesn't change from frame to frame, and that's why we want
But
that
wouldn't
random.
remove point isn't changing frame to frame?
It's removing the point. It's based on this slider.
And once it's gone, it's gone.
Yeah.
Okay.
So yeah. Anything else?
Yep. Another question by Michael. Any particular reason for meshing with VDB from particles instead of the particle fluid surface? Is it a preference thing?
Yeah, I find I have more control over it
Mm-hmm.
doing it with VDB. Particle fluid surface has some great features,
Mm-hmm.
and it's all doing VDB under the hood as far as I know.
Right. Yeah.
But this again, it exposes things a little bit better to me.
Yeah. Particle fluid surface does have VDB options, but you are able to, it's probably lighter as well when you do it like that. I think that's all for questions,
Okay.
everybody. Yeah, okay. Go
Yeah.
for it. Oh, wait, actually, I had one more question.
Sure.
In the flip setup that you have, that's interesting that you're using advect by volumes in the particles,
Mm-hmm.
because you could put the velocity into the volume forces into your flip, but you're choosing to put it via the particles. Is it because that's the motion that you're after?
Um, I hadn't thought about that, but yes, you could totally source volume velocity into in you could source volume velocity into
Mm-hmm.
as a volume source.
Mm-hmm.
Um, I think in this case, I'm actually not using very much of it.
Mm-hmm.
It's if I turn these off, you actually don't see a ton of effect on the flip simulation.
Mm-hmm.
Probably just in terms of being simple, since this is the way I'm doing advection and all the other simulations.
Okay, cool. Thank you.
But yes, you could totally do it that way. All right, and then downstream from the once it's meshed, converting that mesh into polygons again creates some great shapes because it is, it's following our geometry in an interesting way. And then it's important to transfer velocities from those points back onto that mesh. So you can see if I don't do that, there's no velocities. So Any other attributes you want, you would transfer at this stage too, but that's all we need right now. And then that's cached as well. And in our demo cache here, we might as well just go over what that would look like. So we would need, starting off with, we would need our pyro. So a ROP fetch, and we call this pyro advent. And this is a kind of an important thing in PDG too, because this is a simulation. What we do is just copy the ROP we're using here, paste that. And an important part of this is going to be to remember, first of all, copy our frame range to that as well. We want everything to be done by the ROP fetch in PDG, not by our ROP geo. An important thing to keep in mind is if you're running a sim, which in this case in the Pyro it is, be sure to check on all frames in one batch so that they're all done in sequence. Otherwise, PDG will try to run those work items in parallel and you will most likely run out of memory and crash. And I like to color any PDG ROP fetches that are running simulations yellow, just for ease of reference. It wasn't necessary with these because the growth solve, as you remember, was a single cache frame. So it'll just run up to that frame. And glass dissolve is just animated ramps. But downstream from here, it's important to keep track of which are simulations and also the order in which they're being run. So we would want the Pyro sim to be running and then anything below that to wait for it, which in this case would be first the flip points sequence is being very important. ROP fetch. And be sure to name them. I won't set all the parameters. This is just for demo purposes. That also, it's a simulation. So be sure to set that to all frames in one batch. Once those flip points are cached, we got another wait for all. And then the next ROP would be the meshing ROP fetch. And in this case, this can be run in a regular mode where it'll do multiple cache frames at a time. Bearing in mind, though, that you can sometimes run out of memory. So it may be based on how much memory you have and how heavy the meshing is. You may want to also just turn on all frames in one batch just for efficiency reasons. So I usually do this as I'm going. I start to build my PDG cache network just for ease. Does it all make sense?
Yep.
Okay. All right. Okay. Next steps. Going to go back to our master here. And let's do our trails. So these are the kind of smaller foamy particles that are going to be spawned at the end of the lifespan of the flip sim. So let's go through that. So first of all, we're going to set a initial p-scale. These are going to be our source points, and you can see they're taking the shape of our flip simulation. In fact, if we overlay that, you can kind of get an idea of where they're being born from. And I really dig the attribute adjust float um, SOP. It's great. Setting a min value and a max for P scale, but then remapping it with a ramp. So the max value is just a small percentage of the points, and then we have a wider area of our ramp that's kind of in the middle of the range, and then it falls off. If that makes sense. So as you can see here, we've got only a few particles coming in that are larger. You can kind of move that ramp around to change the percentage of larger particles that are being sourced.
A quick question, if possible.
Sure.
Did we see any particles vanishing already? Because you set them up to have a lifespan of 1 second plus minus. I don't know. I don't remember. Did we see some vanishing or not yet?
Oh, are you talking about in this flip simulation?
Yeah.
Oh, let's look at that real quick. In fact, we might as well. It shouldn't take too long to just run a flip book here.
Cool. Thank you, because I was really asking myself that's super interesting.
Yeah, let's look at that. It doesn't look great because you can see it's crinkly but in context, once it's all meshed together with the particles that we're going to spawn from those areas, it actually works pretty well.
I see. Cool. Okay.
Yeah.
Thank you.
No, but thank you for bringing that up because I think I had a note to demonstrate that. So this is a good way to look at just the component of that effect. So there you have it. On your screens, this is probably a little bit jittery.
It looks pretty good.
Yeah.
Mhm.
So yeah, there we have a pretty important component of this effect, not just for the shape and the look when we mesh it all together, but because it actually adds some very interesting velocities to the particles that it's going to be spawning. So, all right. Yeah, thank you for that. Okay. So for the flip trails, there's not a ton going on. We are taking all points, and what that means is we can set how dense we want those points to be spawned just by these two with these two wrangles, the culling points and points by age. So you can think of culling points as the total amount of points, and the cull points by age being the range of where you want them to be spawned from. So next, as in always, we're advecting it. And again, if I set this up to source, this is one of those situations where relative paths are handy, but I'll have to do this. Control C and copy and paste that in there. Build, yeah. Sourcing to velocity with just taking a third of the velocity. And then again, we're adding some upward motion. Now here's a fun expression that I use all the time. This one actually is no longer valid. I'm going to turn that off. It's fun to use smooth expressions, which we covered a little bit, I think, in our last chapter. So what this is doing is I'm actually going to run this forward a little bit and then see the output of this. So yeah, this is the smaller foamy bubbles that are being spawned from the flip. And a couple things, when they're first born, I wanted to get most of the velocity from the flip simulation. Then after that, they were hanging out a little bit. And so I needed a little bit of upward motion towards the end of their lifespan. So what the smooth function does is, actually, let me see if I can do this. So let's have a graph here. It calculates a smoothly interpolating curve from 0 to 1 based on the input. In this case, it's the normalized. This at n age is a built-in attribute for pops that is the normalized age. So whatever age you get it, but it's normalized between 0 and 1. So what this is telling us is at 0.8 of the particle's age, you'll be fully at 1. which means force will be multiplied at its full value of 4, and it will be 0 when the age is 0. That all makes sense. Any questions on that? The effect that
We
has
had
is
a quick question on the velocity you keep sourcing. That's from the pyro, right?
the velocity I'm sourcing into here is actually from the flip simulation.
Aha.
Yeah.
Okay, great. Thank you.
Yeah.
That's from Philip. Yes, N age comes for free.
It does.
Yeah.
Yeah. Now, it appears to me that it's not a built-in attribute with flip particles, but I would have to double check that. I seem to recall that it does not create it, but in POPs, it is a built-in attribute that you can call.
Okay, thank you.
And as you can see, I'm sourcing P scale and velocity. That velocity is coming from those flip points that I'm sourcing, and I'm just inheriting 3/4 of that velocity. And then more velocity is coming from the advection that gives us more interesting kind of shaping. And then towards the end of the lifespan of these points, they're getting some additional upward motion from the pop force, if that all makes sense. And something that's fun to do that you can do on your own also is you can do this with a color. You can add a pop color. I do this all the time too to visualize. It's very handy to visualize some of these things. And if you go to use Vex expression, you can actually just copy and paste. And of course, change this to CD and not multiply and just set it. I believe we can do this.
You don't have to reference like at CD.
I'm so sorry. Yes, thank you.
But yeah.
Yes.
Well, it's still not working.
I'm wondering why I'm. Oh, that's just because it's a vector.
You're right.
Yeah, it should still work.
So Mick is asking the velocity from the flip in the source and then the pyrovel in the advect.
I'm having trouble.
So your pop advect by volumes, that's the pyro?
Yes. We'll come back to color. I'm not sure why that wasn't working.
No worries.
But yes, so this pop advect by volumes is sourcing the pyro.
Okay.
Everything you'll see downstream from here, all the simulations we're running will be sourcing that same pyro for advection. Yeah, actually, let's go ahead and look at this overlaid with the flip, and then you'll see at the end of the flip lifespan, you should see. Actually, not sure why. Oh, well, I do need to select it. So we'll give it a couple seconds here to run up. This is all making sense so far.
Yes. We did have another question about from Philip. Do we need to set the input on the pop color? But if we can return to pop color later after your demo.
Sure,
yeah,
totally. I'm sure I'm missing something very simple. And, but it is handy sometimes to look at those smooth functions as colors. And we're going to be doing a lot of color coding down the line. So here we have it. You can see towards the end of the lifespan of the flip sim, it's spawning smaller particles, and that'll give us, in the context of everything, give us a smooth transition from the solid mesh of the flip and smaller bubbly particles. The other thing I'm doing here is I am adjusting the particle scale, particle scale post sim. This is sometimes easier than doing it in the simulation, just adding a ramp. And what I'm saying is, this ramp is over the normalized age, and it's multiplying to the particles. So they start at zero, basically. They start very small and they get larger. So just smooth them into the flip simulation. So yes. Okay. We have that element. We have our flip. Next, unless there's anything else on that, we'll go over to what I think is kind of the meat of this effect, which is the main bubbles. Okay. So going back to our output, our final here. At this stage, we're going to be looking at these guys right here. The larger and the mid-scale bubbles, which are critical components for this effect. And they're doing some fun things. So first of all, I've got two inputs coming into the bubble simulation here. I've got the points from the growth solve, and I'm also getting the other output from the flip points that we set up. Very similar to the one we used for the more foamy, smaller particles, just slightly different age range. And let's dive inside. Well, first of all, what I'm doing with that is in this case here, a little bit of curl noise actually helped us as well. You can see it adds a kind of a swirliness to, this is the original velocities, and then adding a little bit of animated curl noise to give it some swirly initial motion. And then again, setting an initial particle scale for things, which in this case is just a uniform range. So, and then as the other input, again, just an initial particle scale from the flip source. All right, diving inside, some fun stuff happening here. I'm going to take these out of the pop stream here and just go over them one by one. Remove these. And I'll disable these. This pop stream right here is what's creating the secondary bubbles when they pop. So basically what we want to do is set some rules in this stream, and then based on that, they'll split off into this second stream where they'll burst and create new particles. So we'll talk about how that's going to happen. First of all, let's just look at what we're getting here. Once again, we've got pop advec by volumes. In this case, I actually do have relative path, so we should be good. Let's run forward a little bit. So as I mentioned, we're sourcing from two inputs and coloring them as soon as they're coming in. This is very important. Color coding at this stage is a lifesaver. When you start layering a lot of simulations together, you're really going to want to know what's what, and especially where particles are coming from, what group they belong to. And also we're going to see coloring them based on them changing states or grouping. So the second input is our flip source. And we're just adding a pop color and coloring it green. You can see here I'm setting a just born group. And that just means it creates a group at the moment those particles are born. And that's an optimization because there's no need for me to color the particles at every time step. Even though it's a fast function, it's just more overhead. So it'll color the particles green at the moment they're born and then forget about them. And the same over here with the primary particles. So everything makes sense so far?
Yep. And when you go over those pop advec nodes, could you just continually call out what velocity it's bringing in?
Absolutely.
Okay, perfect.
Yes. So, well, first off, we are bringing in velocity, inheriting velocity from the sources, which is the growth solver with some curl noise and the flip points that we talked about. And I think in the flip one, I'm only getting a third of the velocity from the flip point sources. Other than that, we have setting a constant birth rate. We're not sourcing all points. We can set that just manually here in the constant birth rate. And the life expectancy is set to a high value because we don't want these to die on their own. We want to set all of the lifespan of these points manually. Okay. So next, we don't want them to keep a uniform scale. We want them to start scaling up as they're moving on the y-axis to mimic what bubbles do in a watery medium where there's higher pressure lower down, so they're smaller. And then as they rise toward the surface, they expand because there's less pressure. So we're kind of mimicking that and just doing that with a simple, actually what I'll do is I will do this Hopper angle. First off, just set a min max value based on the particles. Excuse me. Sorry about that. Based on the particle's position in Y. So let's activate that slider. So in this case, we want them to start at a position of around 3 units, which is around here. And then the max is going to be at 12, which is really the edge of our boundary. So 3, 12. That gives us a float attribute. And then that's normalized 0 to 1. So we can use it inside of a ramp, which is the next line. So activate that ramp. And if we back up, along with a multiplier, we want to be working with values that are 0 to 1, but that's too big for the particles we're dealing with. So multiplying the output of that ramp by a slider just gives us a global parameter. In this case, 0.002, I believe. Yes. So let's play that through. And right now, this is just a linear ramp, but we should see them getting bigger in a linear way. Oh, no, actually, they won't yet because we need one more thing. We need to add that at every time step. So p-scale is what it is coming in to the simulation, but at every time step, add y ramp to it.